Hello, my name is Brennan Limar,
My name is Jeffrey Fields.
and this is our heat treatment, hardness, and phase transformations presentation report. To begin, we'd like to mention that unfortunately, our team did lose our data after doing our lab. Therefore, we didn't have anything to write on or write about. However, we were able to get the data from another team's um, lab, and so this enabled us to go on with this presentation. So thank you to Marcus, Jaden, and Thomas for that.
This lab was to investigate how different heat treatment processes like water, oil, and air affect the hardness of selected materials. We did measure the hardness of steel 1018, 1045, and aluminum using Rockwell and Brinell methods. As for our hypothesis, the heat treatment by water increases the steel hardness the most.
So our methodology. And so just running through this, you can see our calibration B. It shows the indenter, the scale, units, and then the weight of the amount of force that was applied to each and every test. And you can see that we have here is our Brinell test. And then also when we combined B and C for that ball and diamond indenter testers with different weights for that. Yep.
For each test, in the data collection for each test, we had to do it three times, and then find the average. And to find the vinyl aluminum test, we use the data that are on the left right side, bottom right side to find the HB for aluminum vinyl test, carbon steel bar.
So the results analysis. So here shown is a bar graph that was created to show what and how much each sample reacted with different tests. So the untreated 1018 steel averaged 89.5 HRB, while air-treated steel measured lower at 65.83 HRB. The water quenched and oil quenched samples showed the highest hardness of 101.67 and HRB and 74.33 HRB. HRC HRC values were much lower for quench samples, and this is believed to be possibly due to the measurements being of errors and scale limitations as well. The Brinell tests on aluminum showed consistent indent size and were used to calculate BHN for mechanical property estimations.
For this discussion, we can say that the water quenching resulted in the highest hardness of 101.67 HRB, followed by the oil quenching of 74.33 HRB, while untreated and air-cooled samples were significantly softer. The result align with the principle that rapid cooling forms harder but more brittle structures, while slowing cooling leads to softer, more ductile phases. Our original data, as mentioned earlier, was lost due to an Excel error. So another team's data was used, introducing uncertainties in testing conditions and potential inconsistencies. The experiment highlighted how controlled heat treatment enhanced material performance and the importance of balancing hardness with ductility in design.
So for our conclusion, results demonstrated that heat treatment has a major impact on the hardness of steel, with the water quenching producing the highest hardness, followed by oil quenching. Air-treated and untreated samples showed lower hardness, consistent with theoretical expectations. Now, despite we lost our data, our analysts, based on another group's results, reflected the same expected outcomes. Improper selection of heat treatment methods enhanced performance, durability, and safety in engineering applications.
For future recommendation, we recommend implementing a more user-friendly tools, for example, digital scanners or optical methods, instead of calipers to measure the indentation diameters more accurately and efficiently. Also, it should be great to include a visual demonstrations, such as videos to showcase the air cooling process and its resulting effect on metal hardness for better understanding and comparison.
So that is our presentation. We hope you enjoyed. And again, thank you to Marcus, Thomas, and Jaden for supplying us with their data from the lab.